wait for the recording to begin. Does anybody have any questions or comments about how the course is developing? Suggestions? Are things going fine with respect to the course? Nothing to share? Do we have ID number 13 present here? To ensure you're there. ID number 13?
Yes, sir.
14? ID number 14, are you there? 15?
Yes, I am here.
Yes, sir. 15.
14 also.
Okay. 16? ID number 16, are you there? 17?
17 here, sir.
18? ID number 18, are you there? Have about 110 students. We will wait for 2 minutes. Again, stabilized. 10. Let's begin this. Once again, is there any question from anyone or whatever we have done till now? No. Question, any comment, query, suggestion about the lecture delivery, course delivery, anything? Hope you find it worth attending the class and have started liking the course content, if not the instructor. Okay, it's absolutely nothing coming from your side. Okay, so to begin with, let us just summarize what we did in the previous class quickly. We introduced the concept of subgroup. Okay, so if you are given a group G, right, a non-empty subset of this group is said to be a subgroup if that subset along with the same binary operation forms a group in itself. Okay, so that is what is a subgroup. And then we sort of started thinking about, so if we have been given a subset of a group and if we are supposed to verify whether it's a subgroup or not, then as of now from the definition it implies we need to verify all the 4 group axioms. Okay, but that is not the case simply because the group operation is the same that was there on the larger set, possibly larger set G. Okay, so first thing we saw is it is enough to check only the closure property and the inverse property. Okay, these 2 properties are satisfied, then the given subset is also a subgroup. Further down the line, what we saw is we could combine both these properties, closure and inverse. Okay, so for every pair of elements AB in the given subset H, all we need to do is to verify if AB inverse, that particular element, is also in the subset H. That is the case, then H is also a subgroup. Finally, we looked at the case where we are given a finite non-empty subset of a group. Okay, in this particular scenario, by checking whether this subset is a subgroup or not, simply boils down to checking only the closure property. Okay, just check if that subset is closed under the same group operation. It is, then it becomes a subset. Okay, so please do remember this condition that a given subset must be finite. Okay, the group in itself may be infinite. Remember, condition is only on the given subset H. Okay. Any questions? I hope all of this is clear. If he has a doubt, now is a good time to ask. Okay, nothing is coming from the other side. It's then I have a question for all of you. What are all the subgroups of Z? I say Z. Remember, I'm sort of doing an abuse of notation. So Z, the set of integers, is equipped with your usual integer addition as the group operation. So can you figure out all subgroups of this group?
Sir, integral multiple of Z. All
Integral multiples of Z.
means when we multiply any integer means 2Z, 3Z. These are subgroups.
Okay. 2Z,
And
3Z,
all other.
all others. So basically, I can write it as say, NZ. Right. So we saw, at least in this particular case, we did, I think, verify to some extent whether 2Z is a subgroup or not. Similarly, of course, there's nothing special about 2. You can replace 2 by 3, 4, whatever you, any integer. Okay, and this n, of course, can be negative as well. So you realize 2Z is the same as minus 2Z. Okay, so which is why this n that is written over here could be any integer. Okay, so these are examples of subgroups of Z. The question really is, see this all is sort of italicized. Okay, so then my question is, can there be any other subgroups of Z? Question clear?
Yes, sir.
Given me, you've listed all of these subgroups. And yes, all of these are subgroups of Z. You can prove it, right? That's not going to be a difficult task. For example, all you need to check is, so NZ is a subgroup or not. You can just look at closure, which will be difficult to verify, and inverse. Okay. So both of these exist. Should be obvious. So therefore, all of these are subgroups. But my question is, can we have any other kinds of subgroups of Z? Okay, I want to list out exhaustively all subgroups of Z.
Sir, Z plus K for all integers K.
Once again, Z
Plus K means Z plus 1, Z plus 2.
What would Z plus 1 be?
Means all the elements are incremented by 1.
So what will you get?
We will get Z. We will get Z itself.
Z itself. So
yes.
Okay, so it's nothing new in some sense. So NZ, right? If I take N to be 1, gives you Z. So this is already included. So let's try to imagine a situation. So what is so special about these NZs is that if I randomly pick two consecutive numbers, right, K1 and K2 in NZ, such that K1, K2 are consecutive elements. I hope you know what do I mean by consecutive elements. Elements in Z. Then what would K2 minus K1 be?
And
It's
N, sir.
N.
same number.
No matter which two consecutive elements you pick, as far as they are consecutive elements, the difference between them will always be N. Right? And in some sense, this is a property of NZ. Right? For any N. So let us try to argue, right, that apart from NZ, there cannot be any subgroups of Z. Okay, so when we say any subset other than NZ, right, what do we actually mean? We mean that let K1, K2, the elements in the subset H that we're trying to see if it is a subgroup or not. The consecutive elements with, let's just say K2 minus K1 equals N, and similarly let P1, P2 belong to H, be consecutive elements with P2 minus P1 equals some M. Right? This would in some sense characterize subsets which are not NZs. Agree?
Yes, sir.
So now let's assume that maybe M is greater than N. I'm not sort of choosing M over N. You can exchange the roles of M and N, right? So if M is greater than N, what can we say?
P2 minus P1 greater than.
Right, and you're just repeating the same thing, right? P2 minus P1 is greater than K2 minus K. Okay? But what I'm trying to say is, since P1 and P2 are consecutive elements, right? What do we mean by consecutive element? It means there is no other element in H which is between P1 and P2, right?
Yes, sir.
So then there exists integers, let's call it Q1 and let's say Q. There exists an integer Q such that Q times M, right? Sorry, Q times N is less than equal to P1. Okay? P1 itself is less than P2. P2 itself would be less than equal to Q plus 1 times N. Try to understand what I'm trying to do over here. Does this make sense?
Sir, how like P2 is less than Q plus 1?
Because if it is not, right? So if Q plus 1n is less than P2, then Q plus 1n will be an element of H or not?
Yeah.
Why?
All the integers with n as product will be part of this nz.
Exactly. Why? Then P2, then Q plus 1n will also be in H. Why?
Then sir, P1 and P2 not remain consecutive.
No, that's true. But my question is, first of all, Q plus 1n. So that's right. So, yeah. But my question, first of all, is why should Q plus 1 times n be in H? If it is in H, and if this is true, then it implies that P1 and P2 cannot be consecutive elements. But if Q plus 1n is not in H, then there is no issue, right? So maybe, okay, first let's reason this thing out.
Sir, I got it. I didn't see that they were consecutive.
No, that's fine. My first question is, see, they will not, I mean, they will be consecutive or will not be consecutive. This question arises if Q plus 1n is in H, right? But do you see why Q plus 1n should be in H?
Because H is subgroup of NZ, and for every Q belongs to Z.
No. Just a minute. H is not a subgroup of NZ.
H is already NZ, means it is a group.
No, H is a subgroup, right? That is what
Yeah,
is
H
the
is
key. H is a subgroup of Z.
Z, yes.
So then,
for yes, if Q belongs to Z, then Q plus 1 is also belongs to Z, and Q plus 1 N can also belongs to H, because it is.
why? Why does Q plus 1n belong to H?
Sir, like she is trying to say Q belongs to Z. So Q
Okay.
plus 1 will also belong to Z.
Right.
And since NQ belongs to NZ, so.
But here we are ignoring NZ, right? Why are you worried about NZ?
H is NZ, right?
H is not NZ, right? That's what we are trying to sort of show. Right? So here H is what? See, what is our aim? Our aim is to show that these are the only possible subgroups. Right? What is special about these kinds of subgroups, NZ? That no matter which two consecutive elements you pick, the difference between them will always be N. But what is the property of H? So we are assuming H is a subgroup of Z. But what is its property? What is this statement trying to tell?
Sir, for two consecutive element.
So K1 and K2 are consecutive elements with difference between them being some N. Okay, this N, don't get confused between these two N's. Okay, if this is causing confusion, maybe I'll change the notation. Okay, let's say A and B. Let A,
B greater than A.
don't want to erase. this P instead of N. QA, right? Okay, so please try to understand. I want to sort of show that NZ is the only possibility, but I'm sort of assuming a contradiction here by saying that let us say H is a subgroup of Z, but which is not like NZ. So what does it mean to say that H is not like NZ? It means that there may exist two pairs of consecutive elements. One is K1, K2, the other is P1, P2, such that the difference between these two different pairs of consecutive elements is different. One is A, the other is B. Now, since they are said to be different, either B will be greater than A or A will be greater than B, one of the two. Right? So this is sort of defining or characterizing a subgroup that does not behave like NZ, isn't it?
Yes, sir.
Yes, sir.
So then what I'm saying is that this P1 and P2 are consecutive elements, right? So there would exist an integer Q such that QA would be less than equal to P1. P1 of course is given to be less than P2. P2 should be less than equal to Q1, Q plus 1A. Right?
Yes,
Because
sir.
P1 and P2 are consecutive elements. Now, this would be a problem if QA and Q plus 1A are in H, isn't it? Do you see the problem?
Yes, sir.
Yes, sir.
So can you justify why should, or can you prove why should Q plus 1A be in H?
Sir, since K2 minus K1 is A and these are included in a subgroup H, so identity element 0 should be in subgroup H and 0 plus n, 0 plus 2n, all that should be in subgroup H.
Good,
So
good.
n time Q times A should be in H.
Right. So see, K2 minus K1, this is something like AB inverse, isn't it? Right, your group operation is plus. So minus K1 is nothing but K1 inverse. So it's nothing but K2 times K1 inverse, isn't it?
Yes,
This
sir.
was the third proposition. Right, so K2 inverse K1, which is A, it has to belong to H. Okay, and since H is a subgroup, so it has to be closed, right? And therefore, QA and Q plus 1A both belong to H. Make sense?
Yes, sir.
Just hearing one person or maybe 5 students participating. The rest, I hope you're following this proof.
Yes, sir.
Since they belong to H, what does it imply? This has to be true. Then what does that mean? What is P2 minus P1?
B, sir.
So P2 minus P1 is B, and therefore from this relation, B has to be less than equal to A. This is a contradiction. Right?
Yes, sir.
Assuming P is greater than A. Therefore, H not a subgroup of G. Make sense?
Yes, sir.
Vandan is forced to reply to or acknowledge my comments on this. Okay, so I'm assuming all of you have understood this. Unfortunately, there is no other way in which I can feel the pulse of the class here.
Sir, in that above inequality that P1 less than P2 and then less than Q plus 1A.
Right.
So first we shouldn't have to say that Q plus 1A belong to H, then we can write this inequality. Like we are guessing it P1 and P2 should be consecutive elements, then we are writing this inequality.
No, but as far as integers is concerned, I mean, Q into A is an integer, Q plus 1 into A is also an integer, right?
Yes, sir.
Okay, so as an relation between integers, this is still true.
Sir, can you explain just once, like why P2 is less than Q plus 1A if B is greater than A? Like why we read that?
Right. So B is greater than A, that's fine. So in that sense, this is counterintuitive. I understand what you're trying to say. Equation 1 is counterintuitive given the fact that B is greater than A. Right? But please remember, P1 and P2 are what kinds of elements? These are consecutive elements.
Consecutive elements in H, right?
Yes.
So, sir, I was asking that only, like, shouldn't we prove that Q plus 1A belongs to H before writing this equation?
Okay, yes. So I think I misunderstood your question. So what I'm trying to say is this would be a problem, right? Equation 1 would be a problem if Q plus 1A is in H.
Yes, sir.
Right, so that is why I then took up this question.
Okay, sir.
So
like
if Q plus 1A is in H, then equation 1 is going to give a contradiction.
Yes, sir, understood.
Okay.
Like the sequence is in different way, that's why I got.
Right. Okay. So I could have written the proof in the slide, but I don't know if you want that, then I would prepare
sir, this is a better way.
Okay. Right. So then please tolerate this sort of a jumbled sequence glitchy. And I'm not memorizing the proofs and writing it. So yeah, once or twice this week. But yeah, I hope now it is clear.
Yes, sir. Thank you, sir.
Okay. So the only subgroups of Z therefore would be NZ. Okay. So now let us try to dig into more details. Okay. So NZ.
Sir, excuse me. Can you show the above slide? The above.
Sure. Yes.
Still one more above. Thank you, sir.
Taking screenshots.
Yes, sir.
Okay. Another question. NZs are the only subgroups. Let's take two subgroups and let's call them PZ and QZ. Okay, so of course, without saying, but maybe I should write here, P and Q are integers. Okay. What happens if I add two such subgroups together? What do I get?
Sir, if
Another
GCD of P and Q is not 0, then we will get another subgroup. And if GCD is 1, then we will not get subgroup.
Come again, if GCD of P and Q
is not 1, means greater than 1, then we will get a subgroup. And if GCD is 1, then we will not get subgroup.
So let us try to see what sort of elements would you find in this set. Okay. Can anybody list out the elements here? So this is after all a set, right? What sort of elements would be there in this set?
So minus 2 times P plus Q.
Minus 2 times P plus Q. Why?
Sir, because in PZ we are having minus 2 times P.
No. But why specifically minus 2?
Means arbitrary.
So arbitrary, how do you write that sort of multiples?
Sir, it can have PZ
times
using
P plus Q.
So,
K
so
times
PZ, right? So PZ contains all multiples of P, right?
Yes.
So let us write it as PK1. Okay, where K1 is an arbitrary integer. Then plus
Q times K1.
K2.
why K1?
QK2.
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 K1 and K2 arbitrary, right? This is the result of adding these two sets, isn't it? Now that you know how the elements of this set can be written, can we just verify whether this subset, this new subset, is a subgroup or not, here without making any assumptions about the relation between P and Q? Right, so let's pick an arbitrary element. Say let A be K1 plus K2 and B be M1 plus QM2. B arbitrary elements of Z plus QZ. Okay.
Sir.
Yes.
Can you please say in which sense are we adding these two subgroups?
Once again, so PZ, QZ are two subgroups and they are sets as well, right?
Yes.
So what is your question then?
Sir, means in which sense are we adding the?
Oh, okay. So right, got your question. So
Sir, it
this
is
a
union
set.
or that?
No,
Union of sets.
No, it's not union. See, thank you. So any element of this subset, right? PZ is also a subset, right? Subset of integers. So, but
Yes, sir.
any element of PZ is also an integer. Any element of QZ is also an integer. So by adding these two, what I am doing is I am adding all elements of PZ with all elements of QZ.
Okay. Sir, means I first I assume that we are adding just the corresponding elements of the sets.
No, but there is no correspondence possible, right? I mean,
means correspondence in the sense that from 0,
okay.
Starting from 0, if we take nth element.
Right. Okay.
I assume
so
that's right.
okay. So thanks for asking. Right. You can see if you don't ask, you will land into trouble. Not just you, you will also put me into trouble. So I had assumed that you knew this. So please, again, request everyone, please ask. Okay? This is the first time I'm teaching you guys. I have no idea what has been taught. Of course, I know you have learned discrete math, but it's just a name, right? I don't have any details. Okay, so is this clear? PZ plus QZ, what it means? Take all elements of PZ, add with all elements of QZ. So which is why K1 and K2 are arbitrary integers. Right, so let's pick two arbitrary elements of this set PZ plus QZ. One of them let's call it A, the other let's call it P. And P. I hope my writing is not too bad. take out what scribbling here. What can you say about A plus B?
It will end the set.
Will be in the set because I can write A plus B as P times K1 plus M1 plus Q times K2 plus M2. Okay, and K1 plus M1, K2 plus M2 are integers, so therefore this will be an element in PZ plus QZ. So what is the conclusion? PZ plus QZ is closed under the group operation.
Yes, sir.
Yes.
Okay, so I'm not writing that. Okay, you can write it. I think that I hope all of you are sitting with a notebook and pen. I think is the best way not to fall asleep, for example, and maybe also to follow what we are doing in class. Okay, what is the next property? If I want to check if this set is a subgroup or not.
Inverse.
Inverse. So again, let A be an arbitrary element, K1 plus QK2 in Z plus QZ. What would be the inverse of this?
Minus PK1 minus QK2, or the inverse of PK1 plus inverse of QK2.
P time minus K1 plus P time minus.
I think you can work this out. This will give you Z. So what is the conclusion?
PZ QZ is a subgroup of set.
That custom to this notation. That's the second result we derived. Now, what happens if we combine this result on this particular slide with the result from this slide?
Sorry, sir. Can you repeat what we do?
Yes. So the question is, so we derived two results, right, about subgroups of Z. One is this. All subgroups of Z are of the form NZ. Okay. On this slide, we derived the result that if I take two subgroups, let's say PZ and QZ, I add them, I am going to get a subgroup of Z again. Right?
Yes, sir.
So what can we say about PZ and QZ? PZ and QZ would also be
Same.
Some n times z.
Exactly. So let's call it D into Z. Right?
Yes.
Yes, sir.
Now what would be this? That's the question now, right? So maybe let's try a few examples. I don't know. So can you give me two random values, one for P, one for Q? Anyone?
2 and 4. 2 and 4.
2Z plus 4Z. Can someone give me few negative integer values in the resultant set and a few positive integer values in this set? 0, of course, will be there because we have shown that it's a subgroup. So identity must be there.
Minus 4. Minus 2. Minus 4. Minus 2.
4, minus 2.
minus 6.
Minus 6. Similarly, on the positive side, of course, this is a subgroup, so I can straight away write 2, 4, 6. So what is this?
It's a 2Z.
It's 2Z. Some other example for P and Q?
Sir, 2, 3.
2 and 3. Again, some positive values, some negative values.
Minus
minus
1.
2, minus
Minus
3.
Minus.
Do you have minus 1
Minus
here?
1. Yes, yes.
Yes,
Minus
sir. Oh, yes, minus 1.
What is this?
1. Z.
This is it.
Does anybody want to try one more example?
5 and 7.
4 and 5.
Which one? 5 and 7 or 4 and 7 or 4 and 5? Okay.
5 and 7.
5 and 7.
Again,
Minus 2.
minus 2.
Minus 5, minus 7.
So I'm not writing this in order.
Sir, minus 4 would be there, I guess.
Minus 4. So once I write minus 2, then yes, it implies minus 4 will also be there, right?
Okay.
Minus 3 will also be there.
3 will also be there.
Minus 1 also.
Once again,
Sir, it will give Z only.
Also be there.
Minus 1, minus 2, minus 3.
how will you get minus 1? Just
21 minus
20
20.
and 21 difference.
20 and 21.
right. Good. This
So, sir, GCD, if GCD is 1, then we will not get Z. And if GCD is 1, then we will
No,
get
but
Z.
here, what is the GCD of 5 and 7?
It's 1.
It's 1.
One.
Right?
1 into
So we will
Z.
get Z. Like
If GCD is 1, you get Z. Otherwise,
If,
we will not
G-
get Z.
if
Means
GCD is
other subgroup of Z.
other
if this,
subgroup of Z.
GCD and Z, I guess.
Means sir, it is GCD times Z.
If GCD is on, then NZ.
So, therefore, I hope you see Z plus QZ. But GCD QZ. Again, so this is our guess, right? I mean, from these 3 examples, right? Guessing is not mathematics. So, we need to prove this. How will you prove?
So we will assume some element in GCD PQ or into Z, like K times GCD of P and Q, and we will prove that it is in PZ plus QZ.
Let's try that. Let A be an element in GCD PQZ. Then
The A can be written as GCD of PQ into K,
GCD PQ times K or
where K belongs to Z.
Z. Okay,
Then, sir, we will write P and Q as GCD of PQ into P1. No, sir. GCD of PQ into A and Q as GCD of PQ into B.
so P is
GCD of PQ into something.
Into something. So let's write that something as M1.
And Q as GCD of PQ times M.
And
then we will find some coefficients of P and Q such that it will give summation as GCD of PQ times K.
Sure, if I understood. Trying to say once more.
Now we will like T1 times P plus T2 times Q will be
T1
equal
Should
to
be equal to A.
A. That we will prove.
How?
Sir, first we will look at left hand side.
T1 P plus T2 Q. Then
Yes, in that we will put value P like GCD PQ times M1.
T1 GCD PQ
We will
M1.
take GCD PQ common.
Okay, so we'll write it common. Common and T1 M1 plus T2 M2 is equal to A, which is GCD PQ K, right?
Yes, sir.
This is cancelled. So
T1 M1 plus T2 M2 equal to K. And sir, T1 M1 T2 M2 all belongs to Z. So for any Z, K belongs to Z, we can find T1 M1 and T2 M2 belongs to Z, for which this equality holds true.
So you're trying to solve for K here, right?
Yes, sir.
So K is in terms of, so this is given, right? P is a multiple of GCD PQ. Q is some multiple of GCD PQ, right?
Yes, sir.
So then you get a value of K. What next?
Sir, for every K, we can find values of P1, M1, P2, M2.
No, but not
So
for
that,
every K here, right? K is some fixed number, right? Because you are writing a particular element of A in this way.
yes, sir. But A is any arbitrary element in Z.
Okay.
So A is any arbitrary element in Z. So for any arbitrary element in Z, we can find T1, M1, T2, M2,
Okay.
which all are belong to Z, such that T1,
So
M1
K
plus
is
T2,
in Z
M2.
and T, right? So this is in Z, no doubt about it.
Then T1, M1 plus T2, M2 would be in Z. Means we can find their values.
Right. So this is in Z.
Sir, I think we are going in wrong way. Like we have to prove like PZ terms from PZ plus QZ belongs to GCD of K. It is belonging all is belonging from Z only. So no encounter of PZ and QZ are there here.
Sir, here I think that T1 and T2 are arbitrary elements. So we can find T1 and T2 such that T1 M1 plus T2 M2 is equal to K. So that T1 P plus T2 Q is equals to A.
T1 P
Means here T1 and T2 we have not fixed, they are arbitrary. So
no, we
means
are supposed to find T1 and T2 here, isn't it?
yes, yes, sir, yes, sir. We are supposed to find T1 and T2 such
Exactly.
that
So you
equality
cannot
holds.
have them arbitrary. So how would you solve this? Do you want some time to do this? should I give you the proof? While I pick up this call, you can try it out. Okay. Okay. Back. Any ideas how to solve this? Okay, maybe. So we already know that Pz plus Qz will be equal to some dz. Of course, we don't know what that d is, right? All right.
Yes.
Yes.
And by the way, what happens if one of these P or Q is 0?
D will be another.
So if P is 0, D will be Q, right? If Q is 0, P will be P. Okay?
Yes.
I hope this much is clear.
Yes, sir.
So, and of course, it is also sense obvious. If P and Q both are 0, P will be 0. Okay, so interesting cases where P is not equal to 0, Q is not equal to 0. Okay?
Yes, sir.
Okay. Now, if I just rename this set, right, because I don't want to keep on writing PZ plus QZ every time I want to mention this, so I'm going to denote it with some S. Okay, now what is S? S is a subset of integers. Okay. So it will have, of course, since P and Q both are non-zeros, S is going to have positive as well as negative integers and 0 as well. Right? So I'm going to pick the smallest positive integer in this set, S. Okay? Let T be the smallest positive integer in S. All right?
Yes, sir.
Okay. Since D is in S, right, I can write D as what? P times is some M0 plus Q times some N0, right? That fine?
Yes, sir.
Yes.
Now, S contains all elements of the form pk1 plus qk2. Okay. For any x in S, I can write x as pk1 plus qk2. Okay. That k1 and k2 are integers. Now, what happens if I pick k1 equals 1 and k2 equals 0? Get
We'll
P,
get
right?
x goes to p.
X is equals to
Right.
P.
And therefore P is in S. And similarly,
Q is in S.
Q is in S. Next, what would be the step? Let us choose divisors of P and Q. Okay. Okay, so let us choose a divisor K, Z. K divides P and K divides Q. Right? What does that imply?
K is a multiple of a GCD of P and Q.
And of course also a multiple of P and Q itself, isn't it?
Yes,
Yes, sir.
yes.
So P can be written as K times
Something.
something. So let's call that something is T1 and Q is K times.
Q times T.
So what can we say about any arbitrary element in the set X? We have already written it as sum K1 plus K2. If I substitute the values for P and Q here, what do I get?
K times some
K
integer.
times.
K times K1 T1 plus K2 T2. Right? So what does this imply?
It is K, sir.
Sorry? Any element of
K is
K is
KZ.
so this
K
is
times
some
Z.
integer. But so what can we say? What is the relation between X and K?
K divides X.
Multiple of GCD.
K divides X. Agree?
Yes, sir.
Yes,
Yes,
sir.
sir.
So any divisor of both P and Q is also a divisor of every element in X, in S, sorry. Right?
Yes, sir.
So therefore, K also divides this special number, this special positive integer that we chose. D.
Yes, sir. Because it exists in A.
Right. So D is in S, right? So, and we have just shown that any divisor of P and Q divides all elements of S. So therefore, K also divides D.
Yes, sir.
So what can we now, what is left to show?
K is maximum divisor.
D is GCD of
D is
P and
GCD.
Q.
So
Maximum
what is,
divisor.
Difference between
see,
two
so
consecutive elements is GCD of PQ.
so in other words, see, D is the smallest positive integer, right?
Yes, sir.
Yes, sir.
Yes,
All
sir.
multiples of D by default are going to be in S, isn't it? Because S is a subgroup.
So can you repeat?
So all I'm trying to say is D is the smallest positive integer in S. S is a subgroup, right? We have already
Yes.
shown that S is a subgroup. So all multiples of D are going to be there.
Yes, sir.
The only thing
Yes.
that is remaining to be shown is, what is it?
D itself is GCD of P and Q.
Yes, and GCD means two things, right? What are the two things?
Uh,
Greatest and common divisor.
Yes.
What have we shown here? What does this imply? This equation or this conclusion 1? What does that imply?
D is common divisor of P and Q.
So does that imply that? What
So
have we shown here?
D is multiple of K.
Exactly. So if there is any common divisor of P and Q, that common divisor also divides D.
And as D is smallest, then it is implies D is equals to K.
No, I mean, there is nothing, I've not assumed anything about K, right? All I've assumed is it's a divisor of both P and Q. I've not assumed it is the greatest, smallest, anything.
Sir, I am saying that as D is the smallest element in S, smallest positive element, and we consider D as some T times K, and as D is smallest, this implies that D should be equal to K.
Yes, sir. K and D are equal.
But there is, so what I'm saying is K is itself a variable, right? Why are you assuming K is something fixed? See, read this point carefully. What does it say? K is any arbitrary integer that divides both P and Q. Right? So there is nothing that says that there can be only one such K.
So K is all common divisors of P.
Exactly. K
Yes,
can be any common divisor of P and Q. So it doesn't make sense to say K is equal to D, right?
yes, sir. Yes.
All we have shown that, if you look at this equation 1 carefully, K is any common divisor of P and Q, right? So all common divisors of P and Q will also divide this D. That is what we have shown.
Yes, sir.
So in some sense, D is greatest, right?
Yes, sir.
Yes, sir.
But what is left to be shown?
It is common divisor.
Common
Common
divisor.
D is greatest common.
Greatest we have already shown. We now, the only thing that needs to be shown is that D divides P and D divides Q. How will you show that? How will you show this?
P should be equal to D times something integer. Then we will show that.
Yeah, so how will you show that P is a multiple of D, right? It's, I mean, the same thing, right? D divides P is the same as saying P is a multiple of D.
Yes. Sorry, sir.
So that's okay. No need to be sorry. See, what is P? P is in S, right? Therefore, P can be written as M times P plus N times Q. And of course, we know it is just 1 times P plus 0 times Q. So maybe, okay, let me not even write. What happens if I divide P by D?
What's the divide P by?
D, this D.
So it will be D times.
D times some number. I don't know. I'm running out of symbol names, but let me try with A. So A is the quotient, okay? Plus there will be in general, right? Remainder. And what is the range that the remainder can take?
0
0
to D minus 1.
P minus 1.
Right, so it's smaller than D. That's the important point to keep in mind. What is A, what is D?
Smallest element.
smallest
Smallest
element,
positive.
and it can be written in this form, right? Pn0
Yeah.
plus Qn0. Let's use that. A plus R, right? So what is R? Equal to, take this on the other side, what do we get?
E
A,
minus
1 minus
AM naught
AM naught times
into P plus
or minus, right?
minus Q AM naught.
N0 Q. Okay, what does this imply? What is 1
R
minus
is in
N0A?
form of R is
Exactly,
of
yes.
form.
Go ahead, Bandhan.
R is in S.
R is in S. Great. But does this imply? Since R is bounded by D minus 1.
R will be 0.
Exactly. If remainder is 0, that implies D divides. And we are done. Follow the argument, or should I repeat this once more?
No, sir, understood.
Anybody else? If you want me to repeat.
Yes, sir. Could you please repeat?
Okay, from what step? I guess from this step.
Yes, sir.
Right. So see, till now this equation suggests that if there is a common divisor of P and Q, that common divisor will also divide D. Okay, that is something we have proved. Now, if we are able to show that D divides P and Q, then we are done, right? Then it basically proves that D is the GCD of P and Q, right? Greatest common divisor. The greatest is from equation 1 or conclusion 1. Common divisor is still left, right? So we need to show that D divides P and D divides Q. Okay, so in order to show that, what we have to show is if I divide P by D, the remainder is 0. Okay, so
Yes.
I'm going to do that division. So in general, if I divide P by D, I get a quotient A and the remainder R. Okay, the constraint on the remainder is that it has to be in this range 0 to D minus 1, right? The remainder is always less than the dividend or whatever that thing is called, I forgot. It's called divisor, right? It's called divisor if I'm not mistaken. So the remainder has to be strictly less than D. Agree?
Yes.
Okay. Now what is special about this D? It is the smallest element in S, right?
Yes.
Since it is an element of S, we can write it as P times this integer n0 plus Q times another integer n0. So that is what I am substituting here. Okay, and then I am trying to get the relation between the remainder and P and Q. So this is what I get. Okay, so I get remainder as some integer times P minus some integer times Q.
Yes, sir. Got it. That how remainder is 0.
Exactly. Okay, good. Anybody else has a doubt? Similarly, we can show that
D divides Q.
Q or D is nothing but GCD for Q. Okay, so that's the proof. This is your proposition number 5. Okay, P and Q are both non-zero, of course, non-zero integers, then pz plus qz has to be dz such that this d divides p and q. I can write this d as an integer times p plus another integer times q, and this d is nothing but the GCD of p and q. Okay. Okay, another question. So I'm giving you two subgroups H1 and H2 of the same group G. Okay. Now these subgroups are also subsets, so therefore I can take set intersection, and with the same group operation, my question is this set also a subgroup of G? And here, although the title of the slide says subgroups of Z, this is a general question. So what do you think? Would H1 intersection H2 for any arbitrary group G be a subgroup? How will you check that?
We check the two properties.
Yes. So which properties? Say closure.
Closure and inverse.
So let A be the two elements in the intersection set. Okay. What can we say about A dot B? Okay, so obviously AB is in the intersection set, so therefore A and B both belong to H1 and A and B belong to H2 as well. And since H1
and H2 are subgroups,
A dot B belongs to H1 and
also H2.
Since H2 is a subgroup of G, A dot B belongs to H2 as well. Therefore, A dot B is in H1 intersection H2. What else do we need to check?
Inverse.
So, how will we show, or how will we verify if this axiom is satisfied or not?
Let A belongs to intersection.
Then same way, right? Since A is in H1,
A inverse will be in H1.
Round. H1 is a subgroup of T, A inverse, which is in H, sorry, it's in H1. And similarly, so I'm writing this in short. I hope you understand what I'm writing here. 2, 4, A inverse is in H1 intersection H2. You can conclude safely that for any arbitrary group, if I give you two subgroups, H1 and H2, then H1 intersection H2 will also be a subgroup of G. Right? I hope this is straightforward, right?
Yes, sir.
Yes, sir.
I leave all of you with this question. Question is, again, come back to subgroups of Z. Let's pick two subgroups, TZ and QZ. Okay. What would be the intersection of these two subgroups? Okay, so from the first
LCM of P and Q times Z.
Okay. LCM. Those of you who think this is LCM, now try to show that it is LCM. Those of you who do not see that it would be an LCM, right, try to take few examples. Okay, and figure out what this would be. But once again, from the examples, maybe you can conclude it is LCM, but that's not enough. You need to prove that. Okay, so I'll stop.
Yes, sir.
we begin with this particular slide in the next class, okay, which happens to be on Tuesday. Right? Thank you, and see you in the next class. Oh, by the way, the tutorial is scheduled for tomorrow. I put out the first handout, the tutorial questions on Moodle today. Okay. Thank you.
Okay, sir. Thank you.